Thank you very much for the invitation. It's a big honor for me to talk here. It's the first time. So all the introduction was already given by Timo, so I don't have to introduce anything. I can go straight to the point. So as we learned from Timo's talk, he introduced motives over a scheme, and as defined by being étale sheaves over the category of smooth varieties over S with values in the derived category of Q vector spaces, and then actually restricting ourselves to the ones which are A1 invariant. And then as a final operation he did, we want to invert the Tate twist. And but now anyone would see that this definition doesn't really make use of any specificity of schemes. One can define the same category replacing schemes with any other object for which it makes sense to talk about smooth things over it. In the same way as one would replace A1 practically with any object in our category, imposing that it becomes contractible.
So there was a subtlety in his talk that he first looked at S of finite type over the integers, and then he extended to, by using some Schrick pullback, and then of course you can just, suppose you take this definition for any S, does it give the same? I'm not sure.
I think that the reason why he stick to that perspective is because he wanted to have the lower Schrick functors and them to behave nicely. But there is no, even for an arbitrary schemes, there is no problem in this definition.
But it does not give the same.
Yeah, you mean either, okay, whatever. So I will use this as a definition for anything. And, but in my talk, S will no longer be a scheme, so I'm away from Timo's territory. It will be an adic space. And for me...
What was the conclusion? Conclusion? It was the same? Is that
No. But let's say I am away, I don't have to have... I will also have some hypotheses on S, but they will be slightly different from Timo's. And I think the reason is that he had to deal with these lower Schrick functors, which are only defined for finite type maps. Anyway, so for me, in my talk, S is an adic space, and for me adic space means that it is locally stably uniform adic space of finite Krull dimension. It's not an IE, it's an actually. But now, so everything works as nice in the sense that we can make sense of smooth things over S. They will be just the ones which are locally étale over a relative ball over S. And we can talk about the étale site in this category, but maybe we have to replace A1 with the closed ball, the relative closed ball, B1S. You may wonder why. A1 would also have been a nice object, but I will stick to this choice. And when doing that, I will maybe emphasize the fact that I'm taking an adic space by placing a ridge before my DM. And to be honest, I'm not so used in using DM, so I will probably use DA, but for me, they are synonyms in this talk. So let me point out that, as Timo already remarked, this category has a universal property in the sense that there is a natural Yoneda functor straight from smooth varieties over S, sending X to the motive of X over S. He defined it also by giving a name to this map. Was it maybe U or F? I don't know. And this was what he denoted by F lower Schrick of 1, or F lower Schrick of, of 1. And so the way it is defined is by Yoneda-ing things into sheaves and then taking their A1 or B1 localization. So this category enjoys a universal property. Every time you have a functor out of this category, which has étale descent and is B1 invariant, and for which the first homology of GM is invertible, is tensor invertible, has dimension 1, then you would automatically get a functor out of this category as well. So the general idea of motives is that they are the bridge between geometry and linear algebra, in the sense that every time you take a reasonable homology or cohomology theory, which enjoys these properties, it is has étale descent and contracts A1 or B1, then it would automatically factor here. And so the one idea is that they are sufficiently close to geometry, so to give rise to a universal realization, but they are sufficiently far from geometry so that allowing you to make some constructions that would not make sense on the purely geometry terms, only on any given realization. But the reason why I introduce motives is not because of this picture. I have a different motivation in mind. So let's say applications in p-adic Hodge theory is that motives give you some sort of mysterious pullback functors that would not exist if we don't construct B1. And to name you a few, so if S is a formal scheme, then we can take its generic fiber and we can take its special fiber. On the one hand, it's as if, so here we have the so-called specialization map, but this map is just a map of topological spaces, or at worst of, or at best of small étale sites. It's not an actual map of ringed spaces. This lives over the residue field, and this would not. And yet, this specialization map, which does not exist in terms of ringed spaces, actually does give a pullback functor from algebraic motives over the special fiber to rigid motives over the generic fiber, as if it existed. And now, for example, there is a map from motives over little k to rigid motives over large k, whenever k, say, is a complete non-Archimedean field, and little k is its residue field. And this is not something which is completely absurd, and it's not the first time people want to construct such a functor. This functor is as old as time, because it's actually one of the very few things that people came up with when they constructed and defined for the first time non-Archimedean rigid geometry. This is the Moski-Waschnitzer functor. Even Moski and Waschnitzer, and then later Berthelot, and then at the same time maybe Berthelot, they tried to lift things from the special fiber and then considering their generic fibers. And the way one would want to, this is a bridge, this is the Moski-Waschnitzer bridge from the special fiber to the generic fiber that allows one to define, say, rigid cohomology very clearly and very canonically and very easily, because the hard part is to, consider lifts of varieties and then taking their generic fibers. Now, another mysterious functor, if S is a perfected space over Fp, then it's as if S, we have the relative Farfontaine curve, which has been already introduced by Eugen, and once again, it's as if there was a functor of this kind. Of course, once again, this cannot exist in the bus.
That's exactly the one he did not introduce.
Well, let me not introduce it either. Anyway, this is in characteristic 0, this is in characteristic P, and yet we have such a thing in the sense that there is a way to move from here to here, at least as motives, when motives are concerned.
So when you mention Mansky-Washlitzner implicitly, it looks like you're saying that you can use dagger-type spaces instead.
Wow, yes. Thank you, Oper. I counted on you for this. And indeed, Mansky-Washlitzner not only chose local lifts, but actually the interest of their theory was to equip them with a dagger structure. But it turns out that also motives do not see the distinction between dagger or non-dagger things. So the actual Mansky-Washlitzner functor will be the one from here to here, where dagger stands for doing the same definition, but for a relatively dagger spaces. Thank you for your question. Okay, so these are my motivations. And there are extra motivations that I will comment on Friday. For instance, the way motives give you a unified, clear way to talk about limit cohomologies. So to unify the constructions of limit Hodge cohomology or Hyodo-Kato cohomology or étale limit cohomology. But I will comment on those on Friday. Today I will stick to these such applications. So I am aware of the fact that this is a very high calorie recipe because I am using rational coefficients, I'm using the étale cohomology, I am contracting B1. And there are other recipes around. If you are intolerant to Q, maybe you want to have only Z. You don't want your S to satisfy all those conditions. You can take this away. But of course, once you take away an ingredient, the recipe has to be balanced by adding further hypotheses here and there, and that you might even lose some flavors. So this is the recipe I prefer. It's the one that has the most powerful properties. For instance, let me go back later. So what are the basic properties I want to comment on? So the first one is that the association S to reach the S is an étale sheaf. And now, contrarily to Timo, I'm really using the pullback functors. And HDAS is completely generated. This is already been commented by Timo. The second one is the six-functor formalism. And again, this is also true in the algebraic case. So maybe I have to mention that all these properties, you can find them in the work with Joseph, Martin, and myself. But some of them are already well known from the initial work by Joseph alone, and some others are known in some other works I did. Anyway, here this is a compendium where you would find anything which is written on this board. Now the six-functor formalism, so in particular, if F is a map from T to S, and if maybe I can even assume that it is of locally finite type, then you have functors F upper star and F lower star, and in case it is locally finite type, you can even have the exceptional ones. You have tensor products, and you have the inner Hom with the usual properties they are endowed, they satisfy. One, if F is moot of relative dimension D, then F upper shriek is the same as F upper star up to twists and shifts, which means in particular that the lower shriek is an adjoint, is the F lower sharp, which is the left adjoint to F upper star up to twists and shifts. And now let me remark that motives, you see, we use the big topos. We take every smooth thing over S, not the small topos, not just étale things over S. This is crucial because for motives, it is extremely easy to construct F lower sharp, the left adjoint to F upper star. The reason is that this is simply induced by composition. That is, if I have something smooth over T and T is smooth over S, I simply send it to the composite map U to S. So it is extremely easy due to the fact that we're enlarging our topos to construct F lower sharp, whereas in, say, étale coefficients or solid coefficients, defining F lower sharp is one of the hardest things to do. Anyway, so this is one of the properties. If F is proper, you want the lower shriek to actually coincide with the lower star. You want to have a projection formula for F lower shriek. I will come back to this. And if F is smooth and proper, you want F lower star to send dualizable objects to dualizable objects. Moreover, you want some gluing or localization. That is, if you have a Zariski closed subspace of S, you want to have exact sequences of functors like that. So all the usual six-functor business. Now another property I want to comment on is the so-called spreading, or the thing I call spreading out, or continuity. What does it tell us is that if S is a weak limit of p-adic spaces S alpha with quasi-compact, quasi-separated transition maps, then the motives over S can be described in terms of motives over each of F alpha. They are simply the union of the motives over each individual piece. And of course, this co-limit is computed in PRL.
Sorry, what's that? This notation?
This weak limit thing, this is a Huber's notation. So this means that the underlying topological spaces are the limits. And also, if you take any point, the K plus of S has a dense, the union of the K pluses alpha will be dense in the K plus here. It has to do with being the actual limit in diamonds. But I will make some very concrete examples as I will comment on the proof of this property. Right. So as
here you assume that S verifies the finiteness conditions that you put.
Yes.
Like, I mean, the nice staggered uniform.
You're trying to change the recipe. It is possible, but I will stick to my recipe. I used it, for instance, to have a compact generation somewhere with this definition. Okay. Now, as I told you, there are different approaches. The most recent one is by Peter Scholze, who gives another take on motives. And in his recipe, these categories will no longer be compactly generated, and yet they will still have some six-functor formalism. So it is what it is. You can take away an ingredient and still have something sensitive. I will use all of them. And now the aim of today will be to give you some proof sketches. The reason is that I want to demystify the realm of motives and try to convince you that all the proofs are very geometric and very easy and very intuitive. At what time did I start?
20 past.
Thank you. Okay, so let me start by 1. And 1 was the fact that it is an étale sheaf and it is compactly generated. So these are easily seen to hold already at the sheaf level. So if I just took this category without considering B1 invariant. So we just, why is that? The fact that sheaves are a sheaf is a theorem of Lurie, and it's somehow not so surprising. The fact that these are compactly generated, so this is compactly generated by the motives of those U's which are quasi-compact, quasi-separated, maybe even affinoid, I don't know. And the reason is that we know in order to test that these things are compact in here, it amounts to show to the fact that the étale cohomology of a direct sum is the étale cohomology of the direct sum of the sheaves, which is something classical in SGA given the finiteness assumption I am using. Now, the trick now is then to prove that taking this B1 localization does not destroy these properties. So why B1 localization doesn't destroy this? Well, if X is quasi-compact, quasi-separated, then even the mapping space from B1X against a direct sum of F will be the same as the direct sum of the mapping spaces of B1X as well as this holds by definition. And the reason why this is true is that B1 is quasi-compact itself. So if X is quasi-compact, then B1X is again quasi-compact. Now, this means that these agrees if and only if these agrees. And in particular, you see that B1 local objects in here, they are closed under direct sums, which tells you dually that the localization sends compact objects to compact objects by formal nonsense. Now, this is a place in which I can tell you why we chose B1 and not A1. If we had chosen A1, A1 would no longer be quasi-compact, and so this property would no longer hold as stated. And so you have to be careful for what you wish for, because if you want to have some cohomology theories which are not B1 invariant and would force you to consider A1, then you would somehow lose this fundamental property, which is not so fundamental, maybe.
So this property fails for Berkovich motives, you said?
Say it again?
For Berkovich motives?
Yeah, we know that they're not compactly generated. I think Schulze makes a point.
But is it because of...
I think it's somehow because of that, yes. I cannot see the pole.
I think it's here, between the...
Oh, thank you so much.
It's a map to Berkovich motives plus universality.
Say it again?
Your theory of originality motives, or your and your Fibers theory, emits a map to Berkovich motives? The one that
maybe the other way around, but it's not. Yeah, I don't want to say stupid things on camera. Maybe we can discuss a bit later. Yeah, I think my intuition is that Berkovich motives are co-localizing subcategory of overconvergent motives inside here. but not a localizing one. So, but I don't know. Anyway, over a field, if you over k plus, the two notions agree. So that we are happy with for that. Okay, so this was a sketch of proof. So this means that B1 local are stable under sums, and hence the localization preserves compact objects, and we win. Okay, so you see the first proof was fairly easy. Let me move to the spreading out.
Oh, you're skipping the six-functor formalism.
I am.
Is that because that's not so easy?
Maybe. No, but because I prefer to do it on the end, at the end, because we use the spreading out to prove the six-functor formalism. But thank you for spoilers, for the spoiling everything. But anyway, so contrarily to 1, this does not hold on sheaves. We really have to use homotopies. Why is that? Because in the scheme world, if I had a similar limit of schemes, then it is true that quasi-compact, quasi-separated smooth things over S are obtained as a union of those defined over some intermediate level, both as objects as well as maps. Not only object descend, but also map descend uniquely, which means that also the two étale sheaves would be the same, and we'll all be happy. So for schemes, this property continuity holds as stated, even at the sheaf level. But for adic spaces, this does not. And
what about the distinction between sheaves and hypersheaves? Which of them verifies this formula?
say it again.
So in Lurie's work, there are sheaves
And hypersheaves.
And which of them satisfy this formula for schemes or for
I think hypersheaves. But maybe I might be wrong. Okay, sheaves. Thank you. Thank you, Dustin. I apologize. I'm sorry. Right, because you have to control all hypercoverage. I don't want to. But I am in the rational world where sheaves. I mean, my sheaves are hypersheaves. I don't really care. And now about adic spaces, this is no longer true, because what are the two basic examples of a weak limit of adic spaces? Well, CP is the limit of the spas of all the finite extensions of QP inside CP. So you see, the reason is that these are all points, and the union of K is definitely dense in CP because it is their completion. Another fundamental situation would be if I take Z to be the zero set of an equation. Well, this again is the intersection of all the U opens in which F is smaller or equal than epsilon. And now for neither of these cases, then it's not true that the étale site of smooth over CP, this is not simply the union of the smooth things over K, and the same here. It does hold for the small étale site. This is okay. And also here, okay, but not for the large site. So it is true that locally any smooth thing over CP is given by a set of polynomials that can all descend to some finite extension of QP, but maps would not descend. So for instance, consider the map from CP t plus or minus 1 hitting CP, sending t to a pi which is in CP but not in the union of the k's. Then there is no way you can make this map descend onto finite levels simply because it cannot. Nonetheless, Nonetheless, you can move it a little bit with some homotopy and choose another guy here which is close to this one, and choose a homotopy, a path that would connect this map to another one which would approximate it but target the the dense subfield given by the union. And that's the whole point of the proof. So let me sketch how the proof goes. Somehow the proof is different in the two situations, because on the left-hand side we have a union of sub-rings, whereas on the right-hand side we have really these are really the risky, that Z is a Zariski closed subset in each one of those opens. So these are all surjective maps at the level of rings, whereas here they are all sub-rings. And the strategy to prove the spreading out is somehow different in the two approaches. So how to prove? So first, we reduce to the case, without loss of generality, we may assume that all these S alphas are spars of R alpha plus, that the ideal of definition is given pi, which is defined over R0 plus, and that S is a spar of RR plus, with R plus being the union of the R pluses completed, and R is just the same thing with pi inverted. There is some bootstrapping to reduce to this situation. And now I want to further reduce to the case in which the R alphas sit inside the subrings of R. How come? Well, by noting that we can replace the S alphas by the S alpha primes given by the spectra of the same thing, but modulo the kernel to R. Well, why is that? Because you see HS alpha prime is a Zariski closed in S alpha, but here we can use localization, the localization triangle. I have some kind of like B Cartesian diagram by localization, we can perceive the category of motives over this closed sub variety as being the localization over the image of J. Lewis Schrick coming from the open complement. And so this will be a iota upper star, and this is a square. And then we pass to the co-limit. So we want eventually to prove that the co-limit over this category is the same as the co-limit over this category, and we show this by proving that the co-limit of this category is 0. This way, this contribution disappears, and this gets identified with that. But why is true? Why is that is true? Why is the co-limit over alpha of such categories equal to 0? Because here, this co-limit is computed in PRL omega, actually. Here, a set of generators is given by affinoid varieties defined over some U alpha. And because the U alpha eventually have an empty intersection, any such generator becomes 0 for alpha sufficiently large, because they're quasi-compact. So at a certain point, they will vanish. And so if the compact generators vanish, then also this co-limit vanish as well in PRL. And so this is, here we use the compact generators.
Yes, so the compact generators lie over some affine domains in U alpha, will become empty when they're in large alpha.
Exactly.
Okay, okay.
And so this identifies this with that. And this already proves the statement in this situation, where it's simply a matter of toying around with the localization triangle. So we are left to dealing with this situation. And as I had mentioned, everything follows from the implicit function theorem. So case 2, we assume then that the S alpha, R alphas are inside R, and then we can use the implicit function theorem. Or actually a corollary of it, stating that if I have a map from a smooth variety over R, which I can assume to be locally given by m plus n coordinates, modded out by m polynomials satisfying the Jacobian criterion, landing in R prime, say it sends x to S and y to T, then there exists a homotopy H from the same ring to R prime B1 over R prime, so R prime with an extra variable, such that H0 simply recovers F and H1 factors over some R alpha. So like I had anticipated, you cannot simply assume that your maps descend, but you can use your implicit function theorem to approximate your map, your original map, with a homotopy so that the other side of the cylinder does factor at finite level for some alpha. Do we all agree that this is the implicit function theorem? Maybe should I spell it out? Well, this map is just a choice of an S and T. So here I have that P of ST is equal to 0 and del P del Y at ST is invertible. And so these are the classical starting point of an implicit function theorem that would tell us that indeed there are power series functions in R prime that would send S to T, and for which P of S, F of S will always be 0. It's just a, so by the implicit function theorem, so because of that, there exists a unique array of converging functions, F1, as many as there are polynomials in R prime x minus s, such that f of x, f of s is t, and p of x, f of x is just constantly equal to 0. And therefore, we can define H to be the map that sends S to S plus S tilde minus S times U for some S tilde, which is in some R alpha, and it is sufficiently close to S so that the functions converge. And T will be sent to F of this thing. Okay, and by definition, with S prime S tilde in some R alpha sufficiently close to S. Okay, so you see, it's at the end of the day, it's just calculus 1 statement. Huh? Calculus 2? Yeah. Now, so the same trick allows you to prove the fact that I had anticipated that dagger motives over S are the same as non-dagger motives over S. If you know what dagger means, good for you. If you don't, I think that Veronica might tell you something about it. And or also, if S is perfectoid over Fp, even perfectoid motives over S are the same as rigid motives over S, so you can perfectoify or deperfectoify as will, at will. And now, I think, even though I haven't really checked carefully, that by using Arabia's result instead of the implicit function theorem, I think this may also show, I will say what it is that formal motives over a formal scheme are the same as motives over the special fiber. Because Arabia tells you that locally, anything smooth over the special fiber admits a smooth lift. And even two maps between two smooth things admit a smooth lift. And such lifting of maps is not unique, but at least there exists a homotopy linking any two lifts of two different maps from the special fiber to the formal scheme level. This is not the way Joseph proved it, but somehow it's nice. I feel like it's nice to see some geometry and some concrete homotopies around that make all the machinery work. That's a very good question. Because a priori this is just very local and there is no higher compatibility that I had. Right. But fortunately, the reason why this is true is that the B1 localization admits a very explicit formula in the sense that if you have your random sheaf, then its localized version will be the sheaf that sends x to f of x times the cube, and then you take the singular or total complex. So let me give you a meaning of this. Now the cube, so if you read Vygotsky or Morel, typically they take a simplicial object, and this would be a simplicial complex. Whereas I prefer to use cubes. What is a cube? Well, a cube of n is simply b of n, and we can see that b of n and bn plus 1 are related by a bunch of maps in both directions that would place the bn thing into either depending, you choose an index and you place it on that face, whereas on the other side you have the canonical projection. This is kind of like a simplicial thing, except that it's called a co-cubical object. And so this is contravariant, so this will be a cubical object. And as for simplicial sets, there is a Doldkan correspondence that would send a cubical thing into a complex. And so this is very, very explicit. And so the proof really uses this explicit formula. I think there is a more conceptual way, but that's the only way I can prove it.
There is a trick that I use in some quantity. It looks like it also works here. So of using rings of Cauchy sequences to reduce to the case of surjection. Once you know the case, the second case, you probably can if you allow certain infinite products, but then they maybe don't satisfy your condition because they have to go to large. This is in the paper of Sesnavicius and Boutier. But anyway, I think it can be adapted to this problem. But it's a trick that I found several years ago.
Okay. I don't know. My proof, let's say, is as old, so old that that was the only that was the most natural approach we had to the problem, which was using this explicit localization formula and construct the explicit map and prove by hand that all homology groups coincide by showing that it is surjective, bijective on homology groups. But I mean, the conceptual proof somehow lies in this. Okay, in the last 10 minutes I have, let me move to the heart of the problem, which is the six-functor formalism. But maybe before moving to the six-functor formalism, maybe it's a good place where to show the existence of this mysterious pullback from a perfected space to the relative Farfontaine curve. So why is that? Well, take your favorite perfected space in characteristic P. So S is a perfectoid over Fp. Now, there is a way to endow every object here with a relative Frobenius. In other words, there is a canonical way to enrich any motive here with an invertible relative Frobenius, which is automatically invertible because we are in rational motives. Now, once we are here, I ignore this extra datum and I use the spreading out. Now, I have embedded S inside, as closed inside the generic fiber. Say S is affinoid of this space. It's the locus where P equals 0. So I can use the spread out along some, this is a Zariski closed set. This is a P equals 0. So I can use the spread out and rewrite it this as being the union of motives over its open neighborhoods. But actually, because Frobenius is acting on this space and is pushing things towards the North Pole, I can simply stick to one given open neighborhood and let Frobenius doing the rest. And I can do this. But now I can use the fact that in PRL omega, limits, finite limits and filtered co-limits commute. So to rewrite this just as rich dA u phi. The reason is they commute, and so once this exits this, it will just disappear because all these are invertible. And then here I can move to the punctured version of u, where I take away S from it, keep track of the Frobenius datum, and now I spread out on the opposite direction. I use Frobenius to cover the whole space, and by doing that I will be able to cover it all except from the South Pole. So this, by étale descent, will be the same as motives over the space that Eugen introduced, y of 0 infinity over S to the Frobenius, which is indeed the relative Farfontaine curve over S, again by étale descent.
Sorry, here you're proving the result of Ayub?
No.
Okay. So
No. That result of Ayub is proven in the same way as you would prove the localization triangle. I'm not comment on that. I have proven the fact that, by mixing all the ingredients I already introduced, you have this mysterious pullback functor from motives over a perfectoid space to motives over its relative Farfontaine curve.
Thank you.
Now, once I still have 18 minutes, don't I?
Sorry. Yes. Could actually also move the middle bar?
Oh, sorry. Oh. Now the six-functor formalism. Now, as we all know, as we learned from SGA or Liu Zheng, Lucas Mann, or Gates Gorey, Rosenblum, there is a standard way to define a six-functor formalism on such a setting. You want to locally be able to decompose every map into, say, an open immersion and a proper map. Define ad hoc your exceptional functors for these two kinds of maps, open immersions and proper maps, and then try to combine them by proving that they are sufficiently compatible. This is somehow the idea. So one needs to define F lower Schrick and F upper Schrick for open maps, open immersions, and proper maps. Well, for proper maps, we are forced to putting F lower Schrick equals to F lower star. And for open immersions, we are somehow forced to impose this localization diagram. Of course, that does not suffice. And then prove a lot of compatibilities, namely proper base change. Maybe a projection formula. And even that the two can be switched as soon as you have a Cartesian square in which one of them is of one kind and the other one is of the other kind. So this will be the standard way to construct a six-functor formalism. Because for adic spaces, we do have this decomposition using Huber's compactification. But this is not what we do in our paper, because we are not really able to handle some of these properties for an general proper maps. We need, at a certain point, to reduce to projective maps. And this means that we cannot use such decompositions. We have to use decompositions into locally closed immersions and smooth maps or proper projective maps. And so there is a slight variation around this. So, but let me pretend that we are doing the same thing and focus on showing you some of the proofs of A, B, and C. Now, let's do one. Let's do A, which is typically called smooth base change or proper base change. Smooth base change for motives is easy. If F was smooth, this is more or less by definition. Both upper stars and lower sharps are very easy to define, are very geometric. So the hard thing, the hard part is to prove it when G is a closed immersion. So actually what we prove is much more general, and we can assume, we may assume, so we prove this compatibility for any quasi-compact map. So since any proper is quasi-compact, we are good.
I'm sorry, what did you just do? You erased.
Sorry, I'm trying to prove the proper base change. So f lower star, g upper star is g upper star, f lower star if f was proper. But actually, it holds a much more general statement, which is the same thing for f quasi-compact. And now I am everything is local in G, so I can decompose my G into smooth and local inclusions and stuff. And the hard part is to prove that this holds when G is a closed immersion. I apologize. Before I had done something wrong. When G is a closed immersion. Now this should be okay. So in other words, I have my commutative diagram, something like this. When this is quasi-compact, and this is a Zariski closed immersion. We may assume that this S prime is given by annihilating global function f. And so what do you think we will be using? Is replacing this horrible Zariski closed with a bunch of open immersions, because open immersions behave much more nicely. And that's what we do. So instead of that, notice that we have a square in PRL where I replace my S prime with my U epsilon, where U epsilon is the locus where F is at most epsilon. And then here I have X epsilon, and here I have F lower star, and here I have J upper star. So the fact that this diagram commutes is again just smooth base change. I told you that in the smooth case this is very easy to handle. The tricky thing is to notice that this is a square in PRL, not in just in infinity categories. And in order to do that, we are using that F lower star is quasi-compact. So as such, it sends quasi-compact objects to quasi-compact objects. Sorry, F upper star sends quasi-compact objects to compact objects to compact objects. And therefore, its right adjoint F lower star does commute with arbitrary sums. So we, again, I want to stress that we are using the fact that these categories are compactly generated. We are using a spreading out technique by approximating closed immersions with open immersions. And the reason why it is in PRL omega, it is because F upper star sends compact objects to compact objects, since F is quasi-compact. All right. Now, I don't have the time to comment on anything else. Maybe just orally. C is actually the hardest of them all. The projection formula somehow can be deduced by the other two in our specific case. And this is really the hardest one. And the way we prove it is by using the six-functor formalism on algebraic motives and using the Moski-Waschnitzer bridge. So we are able to prove C by using those functors that were defined from special fiber onto generic fiber, and somehow deduce it by using the classical six-functor formalism that has been proven for classical algebraic motives. If you are very curious to know the proof, I can comment on it on Friday. Please tell me if you do. Otherwise, I'm finished. Thank you.
Okay, thank you. Are there some questions?
Yeah, I didn't quite understand what was going on the second to last board, the one that's in the middle. So you start with S over FP, but wasn't the result over something over in mixed characteristic that had a special fiber and a generic fiber? I didn't get.
Sorry. So this board is all about if S is perfectoid over Fp, it's as if there was a pullback functor from the relative Farfontaine curve onto S. And we are trying to define its pullback, but only with doing so only on motives. And the way we can do it is by using actually the space Y, or even better, this adic space, and place S inside there as a closed space, and Frobenius, spreading out, push down. By the way, this is you would find it in my joint work with Arthur César.
This specialization map, that's also constructed using this spreading out property, or is it
No, the spreading, this specialization comes from the fact that motives don't see the distinction between formal schemes and their special fibers. And so once you don't see the distinction, if you're on the special fiber, you can go to the formal scheme, and then you take the generic fiber.
So does this construction only depend on the underlying étale topoi, or it actually depends on more geometry? Does it only depend on the étale side of the...
On the big étale side of
no,
S.
the étale side of the rigid variety. The rigid dA.
Yes. So the question is, if I had the map.
Yes, that like.
So for instance, as Timo already suggested, this is insensitive to nil immersions. This fact that formal schemes don't see anything more than the special fiber tells you about it. Then in general, you have to have a map and then maybe prove things, yes. Anything that would hold at the level of étale sheaves would automatically hold typically at the level of motives, because it's simply a restriction, or you just perform a localization starting from the two categories of sheaves. But these sheaves are defined on the big site, on the big étale site over S over T. So you take all smooth things over S with the étale topology.
Yeah, I'm talking about if you change S, is it only depends on the étale site defined by S, or is
by definition, it only depends on the big étale site over S.
Oh, okay.
Okay, if there are no further questions, then let's thank